Today we are looking at how to solve systems of linear equation, and we'll be using Gaussian elimination method. Now we had begun this last time and then stopped it along the way, but now we have to continue with it. Let me load the space. Now first I'll state the procedure of solving system of linear equation using Gaussian elimination. So the first thing you do if you're given a system of linear equation, first thing you do to solve is, let me first of all write the topic, Gaussian elimination. Just a minute. So what are the steps? Is you extract augmented matrix from the given system of linear equation. So once you've extracted the augmented matrix, the next thing you do is to reduce this augmented matrix to echelon form. Reduce the augmented matrix to echelon form. I said we can call this echelon form, or we can say raw echelon form. Raw echelon form. So it means the same thing. So you reduce the matrix to raw echelon form, and then 3, solve. After you've reduced this matrix to echelon form, you solve the resulting system. Solve the resulting system from down going up. Resulting system from down going up. So I want to give you an example so that we see how all these steps are done in an example. So look at an example. And the first example is use Gaussian elimination. Use Gaussian elimination to solve. And the system of linear equation that I want us to solve is just very simple. I want us to solve 2x plus 3y is equals to 7, and 4x plus 7y is equals to 12. So this is a system of linear equation, and I remember I said that when we talk of a system, we mean several linear equations. So this is a linear equation, and this is another linear equation, and so there are several linear equations, and I call that a system of linear equation. Now, so we need to solve this. We said the steps, the first step we do is, first of all, to extract the augmented matrix from this system of linear equation. So let's do that. This is our solution. Now extract the augmented matrix, and we just extract the coefficients of this matrix. and this is for 12. So this is what we call the augmented matrix. So this is the augmented matrix. So we've extracted the augmented matrix. Now, what follows is to reduce this augmented matrix to echelon form, and we use the same steps that we used in our earlier video in reducing the matrix to echelon form. So I want this first entry here, the entry in the first row, first column, to be a 1. I want that entry to be a 1. So the first thing I do is I have to divide row 1 by 2. Divide row 1 by 2. So I want this entry to be a 1. And once this entry becomes a 1, I have to use it to clear the other entries below it, make them 0. So when I do this, dividing row 1 by 2, I have 1 there. Then I have 3 out of 2. You can also use decimals, but I've decided to use fraction here. I have 7 out of 2. So I've divided row 1 by 2. Row 2, I just write it the way it is. I've not touched it, so I just write it the way it is. Now, once I achieve this, once I have this element as a 1, I want to use this element to create zeros below it. So I want a 0 in position of row 2, column 1. Row 2, column 1, because I have a leading 1 in a row in this column 1. So I want elsewhere in column 1 to be 0. So to have a 0 at this point, where 4 is, what I want is, I need the entire row 2 minus 4 multiplied by 1. So the entire row 2 minus 4 multiplied by 1. So this is what I mean. I need this 4 minus 4 multiplied by the entry in row 1. And the entry in row 1 is 1. So when I do this, I get a 0 at this position. Let me write, first of all, what I have in row 1. This is what I have in row 1. And I have 7 out of 2 here. So what does this give me? This gives me a 0 in this position. What about this other position? I want 7 minus 4 multiplied by the entry in row 1. The entry in row 1, column 2, is 3 out of 2. And this gives me 6 in this position, because this will be 4, 2 going to 4 twice. So this 2 times this 3 will be 6. 6 from 7 will be 1. Now, finally, let me look at this position. I have 12 minus 4 multiplied by the entry in row 1, and the entry in row 1 is 7 out of 2. So when I do this, 2 goes into 4 twice. 2 goes here twice. So this is 12 minus 14, which is negative 2. So this matrix now is in echelon form. Let me see what this matrix means. What this matrix means is that the first row means that if I have 1x plus 3 out of 2y, 3 out of 2y, the result will be 7 out of 2. And this other means that if I have, you see, this was the value for x. So 0x plus 1y, 0x plus 1y would give me negative 2. This is what this echelon form of this matrix means. That if I have 1x plus 3 out of 2y, give me 7 out of 2. And 0, 1x plus 1y would give me negative 2. And it's at this point that I said that we would now solve this from bottom going up. We will solve this from bottom going up. We solve this from bottom going up. So we solve the last equation, and then after getting the result there, we use it to solve the last equation. So the last equation just means that y is negative 2. Let me share this because I can see pen is not stable. I can share it and then I can share that and share it. So my pen is so as I said, the first thing as we've done in this example was first of all to extract the augmented matrix. And then after extracting the augmented matrix, we had to reduce the augmented matrix to echelon form. And after reducing this augmented matrix to echelon form, we solve what we finally get from bottom going up, from the last equation as you go up. And so in this example, we've already seen that the last equation says that y is negative 2. So we now proceed to the first equation, substitute the value of y, and get the value of x. So what does the first equation imply? The first equation implies that x is 7 out of 2 minus 3 out of 2y. But our y is negative 2. Our y is negative 2. So let me move this one down. So if our y is negative 2, you see that this 2 and this negative 2 give us negative 1 here. So what do we have? We have 7 out of 2 plus 3, where the LCM is just 2. And this will be 7 plus 6, which is 13 out of 2. 13 out of 2. So we found the value of x and the value of y. What we wanted was the solution to the system. So this system has only one solution. And the solution to this system is, you can write it in column form, the value of x and the value of y. This is the solution to this system. So this system has a unique solution, just one solution. This is a unique solution. So it has one solution. And that one solution, you can write it in either in column form or in a row form. There's no problem. And as I said, this answer can be written in decimal here or in fraction as I've done it. So this is the solution of the system. But we have the value of x and the value of y. But now using them, we come up with the solution to the system. We have other systems that have several solutions, or infinitely many solutions, as we shall see in other examples. So let's look at another example and see how to solve the system. And the example that I want us to solve is, I want us to solve for x. So this example 2, solve for x plus y minus z is 4, 5x plus 2y plus 8z is 15, 3x plus y minus 3z is 1 by Gaussian elimination. So after we are done with this Gaussian elimination, we shall look at another way of solving system of linear equations. Of course, we have several ways, and this is one of the ways. Now, so our solution, therefore, we say that the first thing we do is to extract the augmented matrix. Let's just do that. We just extracting the coefficients here. And this is 5, 2, 8, 15. And this other one gives us 3, 1, -3, and 1. So this is the augmented matrix. From this system, I have 4, 1, -1, 4. Then I have 5, 2, 8, 15. And I have 3, 1, -3, 1. So I want to reduce this to echelon form. Now this matrix here, to reduce to echelon form, as we did earlier, want this element to be 1. Want to make this element to be 1. And there are two ways I can achieve this. The first way I can achieve this is by dividing row 1 by 4. The other way I can achieve this is by subtracting row 3 from row 1. Because you can see 3 subtracted from 4 would be 1. So there are two ways here. Let me take the first way, because it's the one we've been using from the start, where we divide row 1 by 4. So when we do this, row 1 gives me 1, a quarter, and -1/4. And this other point gives me 1. And we've not touched row 2. So I just write it the way it is. We've not touched it. And this one, row 3, also is untouched. So we just write it the way it is. Good. First, once we achieve this 1, we use it to clear the other entries in the column 1. Use it to clear the other entries. So I want this entry to be a 0 and this other one to be a 0. How do you achieve this? And you remember I said it's good to tell us your steps. So I'm now telling my steps that to achieve a 0 in row 2, I will take the current row 2 minus 5 row 1. So the entire row 2 minus 5 row 1 will give me the new row 2. So to get the new row 3, I want this to be a 0, so it means that I take the entire row 3 minus 3 multiplied by row 1. So let's do this and see what we get. Row 1 remains the way it is, just remains the way it is. So let me just first of all share and then share so that my pen does not shake the way it is shaking. But you can see how simple the steps are. Just follow the steps, and I want to do that for 3 other examples so that we can master these steps before we proceed to the other way of solving system linear equations. We have to just master the steps. After you've mastered the steps, you proceed to the other way. Now, so we've already said what we are doing here. We've already said that we want to row 2 minus 5 row 1 and row 3 minus 3 row 1. So let's just do that. So let's begin with the row 2. 5. Let me just do my working here. I hope you cannot mix, you will not confuse. I just want to do my workings from here. So 5 minus 5 multiplied by 1, that gives me 0. 2 minus 5 multiplied by a quarter. You notice that the LCM there will be 4, and this will be 8 minus 5. 8 minus 5. Under the same LCM, remember this is 1. So this will be, the LCM there is 4. So this is 8 minus 5. So this gives us 3 out of 4. And we are here, 8 minus 5 multiplied by negative a quarter. And the LCM is 4. This is 1 here. That 2 minus, that 2 plus 5. Because this minus times that minus is plus. So that 2 plus 5, that is that 7 out of 4. Let's be keen so that we transfer correct values. Lastly, 15 minus 5 multiplied by 1, which is 10. Let me just clear the working, my working. Let me clear my working so that I can use it also for the next row. Because this is not part of the answer. This is just my rough work here. There's no problem clearing it. It's not part of my solution. It's just my working. Okay, now let me now come to row 3. And I have row 3 minus 3 row 1. So that means 3 minus 3 multiplied by 1. That gives me 0 here. Then I have 1 minus 3 multiplied by a quarter. 3 multiplied by a quarter. Here, the LCM is 4 here. And this will be 4 minus 3, which is a quarter. And then I have I'm at this point where I have -3 minus 3 multiplied by -1 out of 4. And the LCM base 4, this will be -12. It is a negative a quarter here, negative a quarter. -3 multiplied by, no, -3 minus 3 multiplied by negative a quarter. So this becomes plus. And this is 9 out of 4. -9 out of 4. -9 out of 4. Because it's -12 plus 3, which is -9 out of 4. And then lastly, we have 1 minus 3 multiplied by this one, multiplied by that one. And this gives us -2. We've achieved the first mission. The first mission was to make this 1 and use it to clear the rest, the other elements in column 1. So now we ignore row 1 and concentrate on the last 2 rows. Create a 1 in this position where I have 3 out of 4. Create a 1 in this position of 3 out of 4. And use that created 1 to clear elements below it. So let's just do that. So that's what I write. What I write is I want to create a 1 in this position. To create a 1 in that position, I need to multiply row 2 because that position is row 2, column 2. I need to multiply the entire row 2 by the reciprocal of 3 out of 4, which is 4 out of 3. So that this times 4 out of 3 gives me 1. So what do I obtain? The first row remains where it is. We've not touched it. It's always good to be keen when transferring these elements. Sometimes you transfer a wrong element. So we'll transfer the exact ones. 1, a quarter, negative, a quarter, and 1. So let's now multiply this by the entire row by 4 out of 3. So 0 times 4 out of 3 gives me 0. This times 4 out of 3 gives me 1. What about this? This was that 7. It was that 7 out of 4. So I just multiply by 4 out of 3. And 4 cancels. I'm left with that 7 out of 3. That's 7 out of 3. What about 10 multiplied by 4 out of 3? That gives me 40 out of 3. And the other row, we've not touched it, so we just write it. Good. So let me clear my working space. Clear this, that I can use it. Now, so we created a 1 in row 2, column 2 position. Create a 1 here. So I want to use this one to create zeros below it. I want I don't want to touch on the elements above this one. The elements in row 1, I not touch them. So I'm using this one only to affect elements below. So I want to get a 0 in this position, and for me to do that, I want to get row 3, the new row 3, I need the old row 3 minus a quarter multiplied by row 2, because the one created is in row 2. The first row remains where it is because we are not touching it. Let's just write it. And let's ensure that we transfer the exact elements, because I noticed that last time we transferred a wrong element and it affected our results. Second row, again, the same. Let's transfer the elements there. That's 7 out of 3. And this was 40 out of 3. Now, so let's now perform what we were supposed to perform. Row 3 minus a quarter, row 2. So this, of course, is 0. A quarter minus a quarter multiplied by 1, again, is 0. Now, where we need to work is here. Let's do it from here. The element in row 3 is negative 9 out of 4. Then minus a quarter multiplied by the element in row 2. And the element in row 2 is that's 7 out of 3. That's 7 out of 3. Notice that the LCM there is 12. This is 4 here, and this is 12. So the LCM there is 12. Let me share again so that my pen is not shaking, because I can see it shaking. I want my pen to be stable so that what I write comes out clearly. Okay, so let me begin by erasing what is not clear there. This was supposed to be the LCM, which is 12. Now, so you just noted that the LCM there is 12. 4 would go here 3 times, so this would be negative 27. Because 7 goes there 3 times. 3 times this is 27. And this is negative 37. So this gives us negative 64 out of 12. We can in fact simplify this, because 4 can go into negative 64, negative 16 times, and 4 can go here 3 times. So that's what I want to write. Negative 16 out of 3. Negative 16 out of 3. Let me remove this and use it for the next working. Now, so just want to move slow so that you see the steps. Just move slow, slow. explains in a slow manner so that you can get the steps. Now let's do this. I have the element in row 3 is -2, and I want to subtract a quarter of row 2. And the element in row 2 is 10 out of 3, no, 40 out of 3. I was about to transfer wrong figure there. 40 out of 3. 4 would go into 40 10 times. So what I have in fact is -2 minus 10 out of 3. And then LCM is 3. This would be -6 minus 10, which is -16 out of 3. So this again is -16 out of 3. So this, we've achieved this. So we need to get a 1 in this position. We want to get a 1 in this position in row 3, column 3 position. So let's erase what we don't require. This was our working. Don't require it. Now, so we want a 1 in this position here. So it appears that we need to multiply -16 out of 3 by the reciprocal, by its reciprocal. So that is row 3 multiplied by row 3 multiplied by -3 out of 16. Row 3 multiplied by -3 out of 16. So row 1 remains where it is. Now, the space here is not enough, so let me try to squeeze. But you can see that. So row 1, we've just written the way it is. Row 2, we just write the way it is. This is 37 out of 3. And this is 40 out of 3. And now it's this one that we're multiplying by -3 out of 16. And this gives me 0 here, another 0 here, a 1 here, and a 1 there. I have my matrix reduced to echelon form. So this is the echelon form of the augmented matrix. Just a minute, I can see that I'm not sharing it. The screen is not being shared. So let me just share it. Sorry for that. Sorry for that. The screen was not being shared from what point? I think it was from this point. From this point, the screen was not being shared. So I just multiplied it. We had already arrived at this point, I think, where I had -16 out of 3 minus 16 out of 3. And I think this is the point where I stopped sharing the screen. So I took row 3 times the reciprocal of -3 out of 16. And row 1, I just wrote the way it was. Row 2, I wrote the way it was. So I multiplied this one by -3 out of 16 to get 1. And this one by -3 out of 16 also to get 1. I think, yeah, that's what I did. I'm sorry for that. I was not sharing the screen at some point. Discovered later. Now, so let me move it down a bit. Just a minute. Just a minute. I was checking my network to see whether it's okay. And I've discovered it's just okay. So let me share and then share. This time I have to remember shares. Yeah, it's shared. The screen is shared. The screen is shared. So you can now continue. Now, so we had already said that our matrix, our augmented matrix, has been reduced to echelon form. So we are about now to solve. So let me just write what this means, what this matrix means. This matrix means that 1x plus a quarter y minus a quarter z gives us 1. And this other one means 0x plus 1y plus 32, no, that is 37 out of 3. Z gives us 40 out of 3. And this other one means 0x plus 0y plus 1z gives us 1. So it's from here that we now solve from bottom going up. some slight problem with my network there. Let me just again share it. My solution. I solved from the bottom. I found that's 1. So I came to this other equation here, where y equals to 40 out of 3 minus 37 out of 2z. Z is 1, and that gave me y to be 1. So I proceeded to this other one, where x equals to 1 minus a quarter y plus a quarter z. But I know what y and z are 1, 1. So that meant that my value of x was 1, my value of y was 1, and my value of z was 1. And so my solution to the system of linear equations becomes 1, 1, 1. So this one is for x, and this one is for y, and this one is for z. So I want to look at a slightly different example that we see how to solve systems of linear equations where we can get unique solutions. For example, in the first 2 examples, we've had unique solutions. Let me try another one and see what we get. Example 3. And this one I want us to solve. We are still using Gaussian elimination, so we're solving x plus 2y minus z equals to 2, and the 2x plus 5y plus 2z equals to -1. That is 2x plus 5y plus 2z equals -1. And then we have 7x plus 17y plus 5z equals -1 by Gaussian elimination. Let me just see whether I've transferred the exact values and it's okay. The values are okay there. Let's solve this system of linear equation. That's what we get. First of all, we extract the augmented matrix. That is 1, 2, that was z, so it's -1. That is 2. This one is 2, 5, 2, -1, 7, 17, 5, -1. We are lucky we already have a 1 in this position, otherwise we would have created it, but we already have it, so we just now use it to create zeros elsewhere in column 1. So we need a 0 in this position and a 0 in this other position. So to get the new row 2, I can see I have a 2 as the first element there. So I would take that 2 times row 1 and subtract from the existing row 2. To get the new row 3, I can see that I have a 7 here, so I need the old row 3 minus 7 multiplied by row 1. So let me just write what I get. That row 1 remains where it is. Row 1 remains the way it is here. And row 2 is minus 2 row 1. So this 2 minus 2 multiplied by row 1. The element in row 1 is 1. So when I subtract that, I'll get a 0. 5 minus 2 multiplied by 4. That gives me 1. Then I have 2 minus 2 multiplied by the element in row 1, which is negative 1. This gives me 4. And I have negative 1 here. Minus 2 multiplied by the element in row 1, which is 2. This gives me negative 5 in its position. Negative 5 there. 7 minus 7 multiplied by this gives me 0. 17 minus 7 multiplied by this. 7 multiplied by this is 14. 14 from this 17, this will be 3. 7 multiplied by negative 1 will be negative 7. Negative 7 subtracted from this 5 will be 12. And then 7 multiplied by this 2 will be 14. 14 subtracted from negative 1 will be negative 15. That's okay. Now, so what we want is a 1 in this position, and luckily we already have it. Otherwise, we would have created a 1 in this position. And once you have this 1 in this position, we use it to create zeros below it. So that is what we want to do, because we already have one here. So we just need the new row 3. So we take the old row 3 minus 3 multiplied by row 2. We will not touch this row 1, so we just write the way it is. We will not touch it. We just write it. Row 2 will not touch it. Let me stop sharing and then share. So the steps of Gaussian elimination are very easy. They are simple steps. They're easy to follow. And you can see that they are the same steps in all the examples that we've done. Let me share it again. Okay, you can now write comfortably. Now, so saying that row 2 remains where it is, I have a 0 there, I have a 1, I have a 4, I have negative 5. I use this row 2 to get the new row 3 by subtracting 3 multiplied by row 2 from row 3. So of course this will be 0. And then 3 minus 3 multiplied by 1 will be 0. 3 multiplied by 4 will be 12. 12 from this 12 will be 0. 3 multiplied by this 5, negative 15, negative 5. 3 multiplied by negative 5 will be negative 15. Negative 15 subtracted from negative 15 will be 0. Now, what is important here is my last row here is very important. For the first time, we have the last row that is 0 from the left to the right. Every element. We have a 0 row for the first time. Let me show you what we got the other row in the other graph so that we see where the difference is. And I've said that this is very important to me. This row is very important. Let's look at this other example. This other example, we had an element here. Or after reducing to echelon form, we had the 1 and then 1. So we had 1, z equals to 1. And this other example, example 1, we had z equals -2. Z equals -2. So the row was not entirely of zeros. The row was not entirely of zeros. But look at the example that we have at hand. The row is entirely of zeros. We have 0 plus 0 plus 0 equals to 0. So when we get that, then it tells us that this system of linear equations has several solutions. We have several solutions. So let's just write what this matrix means. What this matrix means is that we have x plus 2y negative z is equals to 2, and the second one is y plus 4z equals -5. And that this other one is 0 plus 0 is equals to 0. So this system, a system that has this system has infinitely many solutions. This system has several solutions. It's not like the other two that we had unique solutions, just one solution for the system. So now many solutions. So what we do, you notice that we have the leading element here, then the leading one here, but this one has no leading element. So we solve for the leading variables. We solve for the leading variables. So we solve for the leading variables. And the leading variables here are x and y, the ones I've circled. Solve for the leading variables. In terms of the other variables, we call them the free variables. These are the free variables. So the ones that are not leading, the ones that are not leading, does that make sense? The leading variable, so y, and therefore we call it the free variable. So z is the free variable here. So we'll solve for x and y in terms of z. So what we do, we assign parameters, to free variables. We assign parameters to free variables. So a parameter will just be a constant. For example, I can say that let z, which is a free variable, be 1. So if z is 1, I can get the corresponding value for y and the corresponding value for x. I can also say let z be 3. And if z is 3, then I can get the corresponding value of y and the corresponding value of x. So that is why I say that this system has infinitely many solutions. So it depends on what you let your z to be. So if z is let to be negative 1,000, can you find the corresponding value of y? And then find the corresponding value of x. So that is why we say it has infinitely many solutions. So instead of assigning constants, we shall assign parameters, like you can say, let z be t, where t is any number. T could be 1, t could be 3, t could be 1,000, t could be negative 10, and so on. So once you assigned z to be t, and remember that z is a free variable, so that are the free variables that we are assigning parameters. Once you've said that let z be t, you solve this from bottom going up. Solve this from going up. So y, that y be negative 5 minus 4z. But you said z is t. So it's negative 5 minus 4t. Then we come to this other equation. The other equation, you see that x is 2 plus z. So if we were to move this the other side, move this other side, but that is t. And then minus 2y. Minus 2y, but y is negative 5 minus 40. So let's just simplify this. What I see there is 2 plus t, and this plus 10, and this is plus 8t. Okay. We need to some few challenges of network, but it's okay. I think you can see it. Now, what is this? This is 12. The constants here give us 12. Constants give us 12. Let me just erase. Write the 12 properly. The constant give us 12. Now this one I have to unshare the share. The pen is not stable. Going to share, and then let me share it now. So after collecting leg terms, we realize that the constants give us 12. And this one is t plus 8t, which is 9t. These are done. So we have our values of x as 12 plus 9t. And then we have the values of y as negative 5 minus 40. and then the value of z. So what is our solution? For answer, therefore, the value of x was this. Let me just begin with the 9 and g. That is the value of x, and the value of y is negative 40, negative 5. I've just decided to begin with the variables. And then the value of z is t. This is the solution of the system. So that is why I say that this system has infinitely many solutions. And I say that it depends on what you assign your t to be. So if t was to be 1, what would be the solution? If t was to be 2, what would be the solution? But then we just leave our solution this way. We leave our solution this way. You don't need to replace it with constants. You don't need to replace t with 1 or 2 or 3 or 4. Just leave your solution this 4. So you can see we've now tried solving a system that has infinitely many solutions. Let's look at another example. And this example again is a bit different from the other example that we've seen before. Guess this example. And using Gaussian elimination, solve. Using Gaussian elimination solve, I want x plus 10z is equals to 5 and 3x plus y z is equals to negative 1. And then for x plus y plus 6z is equals to, so there's a negative 1 here, there's a 1 here. So we want to solve this using Gaussian elimination. The first thing we do is to extract the augmented matrix. So to extract the augmented matrix here, we need, that is 1. You realize that there's no y, it has 0. And that is 10z, so right. And this is 5. And this one is 3, 1, negative 4, negative 1. And this other one is 4, 1, 6, and then 1. We have the augmented matrix. So this was 4. Let me write it here. This was 4. We have the augmented matrix. Let's reduce this to echelon form. Lucky enough, we already have a 1 in this position. So we use it to create zeros here, where there's a 3, and a 0 where there's a 4. So how do we arrive at row 2? The new row 2. It will be the old row 2 minus 3 multiplied by row 1. And how do we get the new row 3? So it will be the old row 3 minus 4 multiplied by row 1. So what we get, row 1 remains what it is. This is 5. So 3 minus 3 multiplied by 1, that is 0. 3 multiplied by 0 will be 0. Separate from 1, that would be 1. 3 multiplied by 10 will be 30. Subtracted that 30 from negative 4 will be negative 34. and then 3 multiplied by this 15, subtract this 15 from -1 to get -16. Let's come to the third row. 4 multiplied by this 1, subtract from this 4, about 0. 4 multiplied by 0 will be 0, subtract from this 1, the 1. 4 multiplied by 10 will be 40, subtract from 6 will be -34. 4 multiplied by 5 will be 20, subtract from 1 will be -19. Now I have this one. I want to use it now to create a 0 below it. So I know that I'll be taking row 3 just minus row 2. So row 1 remains where it is. Five. Row 2 remains where it is. Now subtract row 2 from row 3. 0 minus 0 will be 0. 1 minus 1 will be 0. To achieve that, this is what we wanted, is 0. -34 minus negative, and -19 minus -16 would be -3. This again, the last row here again is very important. When you compare the other examples we've had, use again is very, because giving a 0. We had some element here, an element here. So this, I arrive at this point. What this tells me that the system that we had, the system of linear equation that we had has no solution. This system has no solution. When I look at the last row of the echelon matrix, when I look at the row of the echelon matrix here, it tells me that the system has no solution, because I cannot have 0x plus 0y plus 0z giving me an non-zero value. You cannot have 0 plus 0 plus 0 plus 0 giving you a non-zero value. So it's supposed to be 0. So when it gives me a non-zero value, it tells me that the system has no solution. So I say this system has no solution, has no solution. Because it is impossible. It is impossible that 0x plus 0y plus 0z would give a non-zero value -3. This is impossible. Because I know that this 0x will be 0, 0y will be 0, 0z will be 0. So when you add 3 zeros, how can you get non-zero value? So it means that the system has no solution. So this is the answer to the question. The question was that is solve the system Gaussian elimination, and we've solved it and found out that in fact that system has no solution. So what this means that in our working today, what we've seen that we can have a system that has a unique solution, like the ones we had in the first two examples. A system that has a unique solution, like the ones we had in the first two examples here. Just a minute. Began from here. Began from. So the first two examples, we had a system that has a unique solution. And you can see how the echelon matrix looked like. We had an non-zero element here and a non-zero, another element. It could be 0 or non-zero. So the element here could be 0 or non-zero. But here it was non-zero element. Here. And here it was either 0 or element greater than 0. So we are looking at the last row. So on the left side of the last row has non-zero element. And the second element here is 0 or non-zero. The element here is 0 or non-zero. And this one is non-zero. Then this system has a unique solution. It has one solution. We saw that in the next example 2. And in example 2, after reducing to a comb, we had this element here and 0. And this element here could be 0 or non-zero. So when this happens, that we have a non-zero element here, and we have an element here which is either 0 or non-zero, then the system would have a unique solution. The system would have a unique solution. Just one solution. Now look what the other, this was the solution. Look at the other example that we did. I want you to look at these examples. We had all the elements in the last row 0. They were all 0. And we say that if this happens, then this system has infinitely many solutions. That's what we wrote here. That is another scenario. So you have a scenario where the system has a unique solution, and a scenario where the system has infinitely many solutions. And this is how we wrote our solution. And then in the last example, we have this echelon form of matrix, where we have this side zeros and this one 3, non-zero. So then this system has solution. This system has no solution, as we've seen. That's good. So let me now give some questions for you to try. Let me give you some questions for you to try. Manager and let share. Let me just unshare and then share, then give you the questions. Good questions because you need to try and see if you can get results. Of course, I'll give you the questions with the answers that you, at your own time, you try and see if you can get the answers I'm giving to you. You try and see if you can get the same answers that I'm giving to you. So I give you the questions, and I give you the answers. You try it at your own time. But it's good to try. And as I said, it's good if you have a question or a comment, you just put in the chat in the section of views, and I can respond to the questions. Those who asked questions last time, the last question, the last lesson, I responded to their questions in the videos. And if you've not subscribed, please do subscribe so that whenever I upload the video, you can see it, automatically without being sent the link. So that you don't need to be sent the link for you to see the videos. Once you subscribe, and just press subscribe, and that will be easier for you. So that whenever I upload a video, you can automatically see it. Now, so the questions here: use Gaussian elimination, use Gaussian elimination to solve the following. Use Gaussian elimination to solve the following. Number one, want us to solve 2x minus 2y plus 3z is 5x plus 2y plus 5z is 7. 2x plus 7y plus 2z is 9. This is the question. 2x minus 2y plus 3z is 5. X plus 2y plus 5z is 7. 2x plus 7y plus 2z is 9. And when you do this, see whether you find your solution as 124 out of 69, 37 out of 69, and 19 out of 23. This is my solution. So try yours and see if you get the same result. Another question. B. I want you to try 2x plus 3y minus z is negative 2. X minus y plus z is 8. 3x minus 2y minus 9z is 9. 3x minus 2y minus 9z is 9. And the answer to this is 4, negative 3, and 1. If you get a different answer, you can ask so that we see, but you can also discuss with your friends. Or if you did not get an answer, you can ask me. You can check mine. Mine could also be wrong. Or I could try to see where you may have gone wrong. Now, I also want you to do this x1 plus 2x2 plus 3x3 plus x4 plus 2x5 plus 2x6 is equals to 2x1 plus 3x2 plus 5x3 plus x4 plus 3x5 plus 3x6 is equals to 4. 3x1 plus 7x2 plus 6x3 plus 2x4 plus x5 plus 2x6 is equals to 10. x1 plus 2x2 just unshare and then share so that I can write comfortably without the pen shaking. Now this was x1 plus 2x2 plus 3x3 plus x4 plus 3x5 plus x6 is equals to 6. Let me see that I've transferred everything. That is x1 plus 2x2 plus 3x3 plus x4 plus 3x5 plus x6 equals 6. Then lastly I have x1 is 2x1 plus 4x2 plus 6x3 plus 2x4 plus 2x5 plus 6x6 is equals to -4. Let me give my result. My answer is my answer to this question is 9, 3 out of 2 S plus 11 out of 4 T. And this other one is 3 minus a half of S plus 3/4 of T. And this other one is -7, negative a half of S, and negative 14 out of 4 T. The other one is S. The other one is 4 plus T. And the last one is T. So this is our X, I don't know if it's X6 or what, but this is X6. It's the result. I have several examples, several questions for you to try at your own time. The other question is x minus 3y plus z equals to 2, negative x plus 2y minus 5z is -5, and 5x minus 13y plus 13z is 16. And my answer to this is 11 minus 13t, 3 minus 40, and t. So this is a system with infinitely many solutions. And E, I have x plus 2y minus z is 3, 2y minus 2z is 1, x minus y plus 2z is 3, and my answer to this is no solution. No solution is my answer to this. I have 2 other questions, 2 more questions for you. I have this 2x minus 3y plus z is 2, 3x minus 4y plus 3z is 7, 2x plus 3y plus 2z is 8. And my answer to this is 11 out of 17, 10 out of 17, and 42 out of 70. That is my answer to this question. And the last question. A plus 2b plus z is 2 no, it's 3a plus 2b minus c, suppose minus c. Because I'm transferring the wrong things here. 3a plus 2b minus c is 1. That's other one. A plus 4b minus 3c is 11. Negative 2a plus 3b plus 5c is 21. That's 21. And what is my answer? My answer is negative 2 4 1. That's my answer. So, and that is how you solve a system of linear equation by Gaussian elimination. And as I said, we have other ways of solving. We'll look at other ways the other video. Thank you.